Welcome to everyone in today's video lecture session on Assembly Language Programming Part 2. Myself, Manas Kumar Parai. The newly joined e-learners are requested to go through my previous video lecture sessions on 8051 microcontroller to easily understand this today's video lecture session. After completion of this course, we'll be able to write the assembly language program using the loop technique and the specific instruction that will be discussed, that is jump and the call instructions. This is the outline of my course. First of all, the assembly language programming using loop technique will be discussed, followed by the conditional and unconditional jump instructions, the 8051 subroutines, and the precautions to be taken during handling of the stacked memory locations are also demonstrated with suitable examples wherever necessary. Sometimes it is necessary to follow a particular sequence of instructions that will be executed repeatedly. So this is known as your loop. The loop action is performed in case of the 8051 microcontroller, that is decrement jump if not equal to 0. And this is the format of the DJNZ instruction, that is DJNZ raised means registered, comma, the level. Okay. So which register is specified, means which register is assigned and which is tagged with the instruction DJNZ, that will be loaded with the value. After that, it will be decremented by 1, and until and unless it reaches the value 0, then this instruction will jump the control to the particular address which is specified by the level. Okay, so this is combined together the instruction that we have already used in case of 8085 microprocessor, that is decrement means DCR instruction was executed. So decrement source by 1. After that, we have used the instruction jump. Jump means it is jump the control unconditionally or conditionally to the particular memory location. Or we have used the instruction DCX, means decrement the register pair by 1. After that, we have used the jump instruction, which will jump the control unconditionally or conditionally. So this is in the case of 8085 microprocessor. But in case of 8051 microcontroller, these two instructions are combined together, and it is one instruction, that is decrement jump, not 0. Okay. So let us take one example. So this program is written to add the value 3 to the accumulator for 9 times. Okay. So accumulator is cleared first. So accumulator is loaded with the value 0, immediate data that will transfer to the accumulator. And the register R2 is assigned as the counter, which is loaded with the value 09. Okay. So I have to add 3 for 9 times. So I am assigning the value 09 first, which will be loaded inside the register R2. After that, we are writing the instruction add A, then the immediate data 03. So 03 will be added with the value accumulator and it will be stored inside the accumulator. Okay. The next instruction is that we have to decrement it. We have to decrement the value which is stored inside the register R2 by 1. And I have to check whether it is 0 or not. So DJNZ R2, then comma again. If it is not equal to 0, then it will again come back to this location and it will execute the instruction add A, comma, has 03. Okay. So it will repeat the process until it will be equal to 0, and that will be for 9 times. It will execute the same instruction. Okay. After that, it will execute the instruction move R5, comma, A. So what is the value stored inside the accumulator, that will be saved inside the register. If we want to repeat the action for more than 256 times, then we will use the inside loop, means we shall use the inner loop and we shall use the outside loop. Okay, so that I can generate the maximum as possible the times that the process will be repeated. Okay, so this is the good example that we have considered over here, that I have to load the accumulator with the value 55x and I have to complement the accumulator for 700 times. Okay, so I have to set the inner loop and I have to set the outside loop. Okay, so first the immediate data 55x, which is loaded inside the accumulator. Then we are selecting the register R3. So it is the outer loop counter. So 10 means actually it is specified in decimal. Whenever I'm not specifying the age, so by default it will be treated as your decimal number, but it is the software directives. Okay, so my suggestion is that you should write with the hex number, as we have already considered here the 55x then you have to write here XX, because we are using the pen and paper, but actually it is the software directives. But where we are writing here without the symbol H or D, it will be treated as your D, means decimal number. Okay, but it is the software directives maintained. So we shall consider it. We shall consider it as your 0A hex. That is the decimal equivalent to your 10. Okay, 46 hex, that's the decimal equivalent to 70, because I have to generate the 700 times the complement of the accumulator. Okay, so R3 is loaded with the value 0A hex, and the inner loop count is considered as your R2, means R2 is the inner counter. So it will be loaded with the value 46 hex. It is nothing but 70 we are loading inside the register R2, which will be treated as your the loop count for the inner state loop. Okay, after that you see that complement CPL A means it will complement the accumulator directly. Then we are writing the instruction DZNZ, because DZNZ is the instruction that will decrement the register value, and it will transfer the control again depending on that value which is stored inside the register R2. So DZNZ R2 means R2 will be decremented by 1, and whether it is not equal to 0, then it will again come back to its again, means it will again execute the instruction CPL A, means complement A. Now it is coming from this loop, and it will execute the instruction DZNZ R3 comma next. So R3 will be decremented by 1 now. Okay, so it will decrement the value whether it is finding it is equal to 0 or not. Depending on that, it will transfer the control to the next, means this location. Again, it will load the value 46x inside the register R2. So this process will be repeated for 10 times. Okay, so 70 means from this inner loop, it will rotate for 70 times, and outside loop will create the 10 times of the same function. So therefore we are getting 70 multiplied by 10, so 700 times it is complementing the value which is stored inside the accumulator. But don't forget this concept that whenever I'm writing using the pen and paper, I shall specify the hex value inside the counter. Okay, so it is the good practice. Now the conditional jump will be specified. Jump only if a certain condition is met, then I shall write the instruction JZ, then level. Okay, so JZ means jump is equal to 0. Okay, so it is only this instruction JZ is associated to only the accumulator, only the register accumulator. Okay, so now no other the registers are involved with this operation. So JZ is only used for the register A. So mind it, don't forget this concept. So one example is considered over here, the move A comma R0. So R0 is loaded inside the value accumulator. Then JZ over is the level, means it will jump depending on that value which is stored inside the accumulator, whether it is 0 or not. If it is 0, if 0, then it will jump to this location. Otherwise, it will execute the next instruction. So next instruction is R1, which is loaded inside the accumulator, and then the instruction ZZ will be executed next time. Then it will find whether the value of this accumulator is 0 or not. So depending on that, it will decide whether to jump in this particular location or to execute the next instruction, which is written after the instruction JZ. Okay. So here is the another example that we have considered, that determine if R5 contains the value 0, means whether the value which is stored inside the register R5 is equal to 0 or not. Okay, if so, then put 5 hex in it. So what is the function specified is that if it is 0, then you have to put the value 5x inside it. So first of all, I have to transfer the content inside the register R5 to the accumulator so that I can use the instruction ZZ. So move A comma R5, it will copy the content which is stored inside the register R5 inside the accumulator. Okay, then JZ next means it will decide that whether it is not 0, then it will jump to this next location, means this location. Otherwise, it will execute move R5 comma hash 55x, means the 55 will be loaded directly inside the register R5. Whether it is 0, then it will load this, it will execute this instruction, it will load the value 55x inside the R5, and if it is not 0, then it will jump to the location which is specified inside this next location. Okay, so here the conditional jumps are also the instructions are also used by 8051 microcontroller. So all these instructions are the conditionally jump instruction that is used by the 8051 microcontroller. But remember that things, all the conditional jumps are the short jumps, because the address means what the target address we are specifying inside the level, that will be within this range, means 128 to plus 127 bytes of the content of the program counter. Okay, so this limit will be considered, means you have to consider the address which is specified after the instruction, these instructions, that will be within this range. So don't forget this concept. Then the unconditional jump is also used in case of 8051 microcontroller. That is, unconditional jump means which control the transfer unconditionally to the target location. So two instructions are commonly used, that is long jump, L jump, and the short jump. The short jump was discussed in lesson 3, but the long jump means it is unconditional jump. So it is 3-byte instruction. So first the byte which is specifying the opcode, and the second and third byte they represent the 16-bit target address. Okay, so it will jump the control within the memory location starting from 0000 to FFFFX. Okay, so any memory location you can access with this instruction. L jump means long jump. But the short jump is also used in your program, but it is 2-byte instructions. Okay, so first byte is the opcode and second byte is the relative target address. Okay, so relative target address means it will be from 200 to FF, means forward plus 127 and the backward 128 bytes from the current program counter location. You can jump it. But what is the advantage by getting that? It is 2-byte instruction, so you can reduce the size of the memory, means you can you can manage the space inside your ROM memory location, because LJAM is 3-byte instruction and it is 2-byte instruction. Okay, so you can reduce you can manage the space inside the ROM memory location. The next one is the how to calculate the short jump address. Okay, so calculate the short jump address means, actually short jump address means the S jump, the jump if no carry, the jump is 0. All these instructions, then the second byte which is specifying that it is the relative address. Okay, so the program counter of the instruction immediately below the jump instruction, and the target address is not more than 128 or the plus 127 bytes from the address below this short jump instruction. Okay, so if we by mistake we are writing this location or the address relative address which is outside of this range, the assembler will generate an error. Okay, so let us consider one example like that. So we are writing the program, and inside of this program we are writing the instruction like JZ next, JNC over, JNC again, and the SJump here. So next means JZ next means, so it will jump, it will check whether it is equal to 0, the value inside the accumulator is 0. So depending on that value which is stored inside the accumulator, it will transfer the control in the address next, which is specified in the level next, that is 0009 in the ROM location. Okay, now how to calculate this one? You see that JZ next means 60 is the opcode and 03 is the 60 and 03. 03 is the operand. Okay, so 03 is now added with the value 06. Okay, 06 means it is the actually the program counter, content of the program counter which is specifying the particular ROM location. So 06 will be added with the value 03, it will generate 09. So my newly generated address will be 0009. So JZ, it will jump to the location 0009. Okay, here JNC over, similarly we are generating the address by adding the value 05 with 0D. So if we add these two, then we are finding the value, it is coming 0012. So it will jump to this location 0012 where the level is over is given. Okay, so JNC over means it will find the address 0012, and I have to calculate the address by adding these two 1, okay, as it is specified. After that, JNC again, the address is calculated like that. JNC again means I have to calculate, means JNC again, so 0013, then 0014, these two bytes are blocked by this instruction JNC again. After that, the program counter is entering into this location 0015, so 0015. 15 is added with the value F2, then we are getting the value 07. So 0007 will be the address where my controller will jump. So JNC, so again means it will jump to this particular location which is specified inside the program counter, right? 0007. Okay, it is the RAM memory location 0007, where my controller will be transferred. Now this is this SJump here. Here is the level, then SJump here. How to calculate the address 0015? Then what is the opcode for that SJump? That is 80, and FE is the relative address. Okay, so how to calculate it? The program counter is entering into the location 0016 where FE is loaded. After that, the program counter is indicating the location 0017. So now the address level 0017 plus FE, if we add FE with this value, then we'll get this 115. So what is FE? Actually, FE is -2, means we are getting the 2's complement form of 2, means it is -2 is indicated by FE. Whenever it is added with this 1, so we are generating actually 17 minus 2, then it will be equal to 15. So 15 means 0015 is the location where the SJump here will be executed, then it will transfer the control to this location 0015. Okay, but you have to remember it whether the address is within the range -28 to 127 byte, which is associated with the instruction below the SJump. Okay, so now it is valid because the address is within this range. So let us discuss the subroutine concept. Okay, so call instruction is used to call a subroutine. As we know that the subroutine means it is the part of the program which will be executed repeatedly. Okay, so more than once it is executed, then we shall write inside the subroutine. Then main program, I shall write an instruction so that it will call the subroutine. Again, from the subroutine it will jump to this location. These two instructions are used in case of 8051, that is L call, that is long call, and A call means the absolute call. These are frequently used inside the microcontroller 8051 programming technique to call the particular subroutine. Okay, so L call is 3-byte instruction. The first byte is actually the opcode. The second and third byte are used to indicate the particular address of the particular address of the target subroutine. Okay, so subroutine 16-bit address means the subroutine is located anywhere, means anywhere within the range 64 kilobyte of the address space. From this 64 kilobyte of the memory space, I can call using the instruction L call, which is a long call. Okay, but the A call means it is actually the 2-byte instruction, so I can reduce the instruction. The function is same, but what the advantage we are getting, that it is 2-byte instruction, so it will occupy the memory space lesser than the instruction L call. Actually, it is 11 bits are used to address, so the address 2 kilobyte range will be accessed by this instruction A call, means the absolute call. Okay, so now let us consider one example. Whenever the subroutine is called, the control is transferred to that subroutine, where the particular memory location is specified with this instruction L call. The controller will jump to this particular location and it will execute the subroutine. And what the function it will do, that it will save on the stack the next address of the instruction, which is immediately below the long call instructions. Okay, so that whenever I'm just coming from the main program to the subroutine, I have to indicate the next address where to jump from the subroutine to the main program. Okay, so it begins to fetch the instruction from a new location, okay, which is specified inside the L call, which is tagged with the L call instructions. Okay, So after finishing the execution of the subroutine, I have to write the instruction RET, means return, so that it will execute the instruction and it will come back to this particular position, particular memory location where from I have to execute my main program. Okay. So it is the commonly used the subroutine, that is L call, that subroutine 1. So I shall write the instructions. After that I'll write one return. Similarly for subroutine 2, I shall write the last instruction, that is return. For subroutine 3, I shall write the instruction return. So upon execution of this instruction return, it will come back to this particular location. Means immediately after the instruction which will be executed, and this address will be retrieved from the stack. Okay, so this concept will be delivered now. Now, what is the location in the stack that I have to check it? So whenever it is executing this one, I can write the push instruction inside the delay. I can write the pop instruction in this one. Okay. So whenever inside the delay, means I'm introducing these two instructions, push 4, push 5, and pop 5 and pop 4. So first of all, whenever it is calling the instruction L called delay, it will load the value, means it will load 000B, which is the memory location for the instruction move A, has 0A hex, because I have to come back from this subroutine and I have to target this location. So therefore this the memory location will be saved inside the stack. So inside the stack means 08, means whenever the push instruction is executed, the L call instruction is executed, then it will transfer the value 0B, means the lower byte will be transferred first, then the upper byte. Then 00 will be transferred inside the memory location, inside the stack location 09. Okay. Now the stack pointer is indicating the memory location 09. Then whenever it is entering into the delay program, then it is finding the instruction push 4. Push 4 means the value what is stored inside the register. Means what push 4 means, what is the value it is getting, that will be loaded inside the means R5, R4. The content of the R4 will be loaded inside the stack. So now the stack will be incremented by 1. It is indicating the memory location 0A. Now 0A will be loaded with the value 99, because move R4 is 99H. Okay, so 99 will be loaded inside 0A. After that, it will execute the instruction push 5, means R5 will be loaded inside the next memory location. So program counter will be incremented by 1. Now it is indicating, the stack pointer will be incremented by 1, and it will indicate the location 0B, where 0B will be loaded with the value 67. Okay. So now I am just pushing the value of R4 and R5 in two consecutive locations in stack. Okay. Next, the instructions are written over here to produce the certain amount of delay. After that, we are executing the pop instruction. Pop 5 means what is the top of the stack location, that will be retrieved fast. Means pop 5 means it will retrieve the data. The retrieve the data means the 67 will be retrieved fast, and it will come back to this register R5 again. And what is the next location? Means once it is retrieved, then it will indicate the next location. The stack pointer will be indicating the next location. The 99 will be again retrieved in the register R4. After that, it is executing the instruction return, RET, return. So return, whenever the instruction return is executed, then the program counter will be loaded with the means lowered 00, then 0B, so 0V and 00. So 00 will be retrieved fast, then the stack pointer will be decremented by 1, then 0B will be retrieved. Okay, so 000B. So this is the actual program counter, means the program counter will be loaded with the value 000B. So it is indicating the particular ROM memory location 000B. Now it is finding instruction move A, hash 0AA hex. So it is the instruction. Now it will be executed. Okay. So after coming back from the subroutine, it is entering into this instruction, means into this location where it is finding the instruction, and it will be executed. So step by step it will be executed. So the L call we have already discussed. Now it is the absolute call. So in L call, we can access the memory location starting from 0000 hex to FFFFX. So 64 kilobyte of the address we can access with this instruction call, but it's 3-byte instruction. The target address of call must be within the limit of 2 kilobyte range that we have already discussed now. The use of call is instead of call that you can save the number of bytes inside the program ROM space, because it is 2-byte instruction, so you can save one memory space by using call instead of the call. But limit is that we have to access within the limit of 2 kilobyte range on the memory location. Okay. So the call instruction is written over here, that once we are the same program we have considered, that once we are providing the data 55hex, which is available in the port 1, then we are providing the once complemented data in the port 1. Then against SJump back, means this process will be repeated. That what is the program that we have just now discussed. Now see that the program is written again to reduce the number of instruction sets. Okay, org0 and end, these are two the software directives. So what is the main program that we are using the pen and paper to write the program, like move a 55hex. Then where we are using 0AA hex, whenever the instruction complement A is available, means we can complement the accumulator directly. So once we are providing the data 55hex, then accumulator value is now loaded inside the port. So in port 1 the data is available. Then we are just calling the delay subroutine by using the instruction call delay. Then CPLA means complement the accumulator. So it can now complement directly the value which was provided earlier. Then SJump back means again it will come back to this location. Again it will means the accumulator will just save the data inside the program port 1. Again a call delay. So loop will be means again and again the loop will be repeatedly executed. Okay, so therefore once the data we have provided, then it will be complemented again and again with this one. So now from this written program we can reduce the number of the instruction sets. Okay, so here we are generating the particular amount of delay whenever I'm using the crystal outside of this microcontroller. Okay, so length of the machine cycle, now already you are familiar with the machine cycle. So CPU that is executing an instruction takes a certain number of the clock pulse. Okay, so these are referred to your machine cycles. So in original 8051 microcontroller, one machine cycle lasts for 12 oscillatory periods. Okay, so if I am using the clock which will generate the clock frequency of 11.0592 megahertz as it is available in the market, with this range 11.0592 instead of 12 megahertz crystal. So the first one, if the machine cycle lasts for 12 oscillatory periods, then 11.0592 divided by 2 means that is that much amount of the kilohertz that we are generating. So machine cycle is calculated on the basis of that actually 1 by this one means what is the time period that will be reciprocal of this frequency. So 1 by this one is equal to 1.085. So one machine cycle will take 1.085 microsecond time. So to execute the instruction, which is taking the machine cycle of one machine cycle, then the time to execute the instruction will be equal to your 1.085 microsecond. So here few examples have been considered over here. So depending on that number of machine cycle, that will be the time, the execution time will be calculated. Okay, so machine cycle 1, so it will be 1 multiplied by 1.085 microseconds, so it will be 1.085 microseconds. Similarly, the last instruction multiplication of AB, then machine cycle requirement of the machine cycle is equal to 4, so it will be 4 multiplied by 1.085, so it will be 4.34 microsecond. So the crystal that we are connecting with the microcontroller, it will surely means what is the time to execute the instruction, it will surely depends on the particular crystal that we are connecting with the microcontroller chip. Okay, so here we are just calculating the delay. We are writing a program like that. So what is the delay it is producing over here? So this program, the same program we have considered over here, but you see that whenever I'm just writing the instructions to write the delay program, I shall write the instruction move R3 say 200. So 200 is actually the decimal number. It is going inside the register R3. So it is the decimal number. If you consider the hex, so it will be within the 2-byte number. So it is valid instruction, but it is actually the software directive. So whenever I'm not writing anything with this one, so it will be treated as your decimal number. So R3 is loaded with the value 200. After that, the instruction designz R3 here, that will be executed. So it will execute the instruction until and unless R3 is equal to 0. So we are executing, and see that what is the number of machine cycles are required over here. So here, for executing this instruction, machine cycle 1, the second instruction takes 2 machine cycles, 2, return 2. So 200 means 200 times it is taking, it is just rotating inside this one is loop. Okay. So therefore 200 multiplied by 2 plus 1 plus 2 means this one, and so you say that return means it will execute this one for 200 times. So 200 multiplied by 2, then 1 plus 2 multiplied by overall the 1.085, so it will be equal to this one. So it is your, this is your total time delay that will be produced by this program. Okay. After that, you find that the size of the delay that we can increase by incorporating the NOV, means no operation instructions inside the program. So it will take 1 machine cycle. So accordingly, we have to calculate the amount of delay it is producing over here. Okay. So this is the program that is written to indicate that the large amount of the delay will be produced by the nested loop. Okay. So this is the program we have written here. The nested loop we have incorporated inside the program, so that you see that here, and then no operation, it will take only one, no operation, only 1 machine cycle. The designz R3 here, and what is the value stored in R3 means R3 means here it is 250. It is also in decimal number 250. Then it will be decremented by 1. So 250 times this loop will be executed. Okay. So see that 2 machine cycle plus 1 plus 1. So 4 machine cycles are, means it is executed. Then the total time delay for executing this loop is equal to 4 multiplied by 250 multiplied by 1.085 microsecond. That is equal to this one. Okay. Again, you see that again loop repeats here. It means again, whenever R3 is equal to 0 is coming back to this instruction, designz R2 again, then R2 will be decremented by 1, and it will again come back to this particular memory location. Again, it will load the value 250. So this process will be executed for 200 times. Okay. So we have to multiply it, means 200 times, we have to multiply it by 200 times the 1.085 microsecond, this one, because inside the loop will be executed for 200 times. So 200 multiplied by this one, it will generate dash amount of delay. After that, move R3 to 50 means this instruction will take some time. The first instruction will take time, and return instruction will take some time. Okay. So if we add together all this value, means here 1 plus 1 plus 2, okay, plus this inside and outside loop, then the total amount of delay that will be produced by the program, that will be calculated. Okay. So it is very simple. On the basis of this machine cycle, I shall have to multiply with the value 1.085 microsecond, because we have already calculated over here. If the clock frequency is 11.0592 megahertz, then means each machine cycle will take 1.085 microsecond. So execution time is calculated on the basis of the particular frequency that is generated from the crystal which is connected with the 8051 microcontroller. Okay. So this is the summary of that discussion. So we have discussed about the assembly language programming. This is the second part of the assembly language programming technique that we have already discussed over here. So here we have discussed about the looping technique, and few specific instructions like the jump and the calls instructions have been shown over here. The addressing mode will be discussed in the next lecture sessions. So to get the notification of the next lesson, kindly like, kindly subscribe my channel. Thank you everyone. Thank you for watching my video.